In the last video, we explored average velocity some more. And at the end, we were left with the question, well, what happens if the velocity is changing? So here I made a position time graph, and we have some experimentally obtained positions plotted against their time, the times at which we measured them. And you can see intuitively here, if I were to just try to draw some sort of curve through it, it wouldn't be a straight line. So this is not an example of uniform motion. So intuitively here we can say the velocity is changing because I can look at any successive interval, and if I were to just join a segment here to get an average velocity over that interval, we can see that the slope changes as we go along. So that means that this is not uniform motion. But let's say that it's really important to us that we know that we would like to characterize how fast an object is going at exactly t = 3 seconds. Well, we've got a bit of a problem with our definition of average velocity here. You'll remember that average velocity is defined to be the displacement over the time it took to do that displacement. Well, if I just look at this one point right here, I'm in trouble because I would be sticking in 4 meters as my final position. I would subtract 4 meters as my initial position. I would be dividing by 3 seconds by 3 seconds. Oh crap, that's 0 over 0, which is an undefined form. So I can't just blithely use our definition of average velocity if I want to say what's happening at exactly this point. So we can't do that. All we can do is come up with an approximation to how fast we're going. And the recipe for doing that would be to pick a point on either side. Pick 2 times, one before the interval in question, one after the interval in question. For technical reasons, you actually make fewer mistakes if you don't actually pick the time in question. That gets a little beyond where I want to go with this, but just take my word for it that usually you want to pick a point on either side of the time you're interested in. So I picked 3 possible time intervals for which we could compute average velocity. So we've got the ones I've marked here in pink, we've got the ones I've marked here in green, then we've got the ones I've marked here in blue. I can calculate an average velocity over any of those intervals, but what I want would be the average velocity that would be most representative of what is happening at exactly t = 3 seconds. So for a bit of a pause and ponder here, I want you to I want you to tell me which of these intervals would give me the most accurate representation of what's happening at exactly t = 3 seconds, the pink, the green, or the blue. So go ahead and pause the video and then we'll get back. All right. It turns out that our best choice is going to be the blue pair. And why is that? Well, you might be tempted saying, well, if I look over a long interval, I've got a big change. The math would look really nice and all that, but the problem is that it would, if we look at this, we traveled 7 meters in 6 seconds to the left, okay? Whereas in this period right here, we traveled 2 meters in 1 second. So if we use this time interval here is going to give me a shade over 1 meter per second to the left. And this is going to give me more like 2 meters per second to the left. So that's a pretty big difference. So why is this 2 meter per second number a better number? It's a better number simply because we're looking at points that are as close in time to the one that we care about as possible. So the motion here and the motion here, although not identical to the motion here, hasn't changed as much as it has by the time we get over here or over there. So this is where the motion is most similar. These 2 points here are where the motion is most similar to the point here. And like I said, I don't want to get into the technical weeds about why we don't ever use the point itself, but it turns out that it's more accurate if you can look at what happened just before and just after, because it allows you to look across time better. Okay. So with this, with this idea, and say, well, could I get it even better? If we're just using experimental data, no. This is as good as I've got. But a lot of times we can come up with functional forms, or we have a lot better data than this. In this case, what we can do is we can imagine characterizing this as the limit. So we'll define the instantaneous velocity, so no bar here because we're not taking an average. We'll define this as the limit as our time interval goes to 0 of the displacement over the time. So in this recipe, we might first start with this and get a number, and then this and get a number, and then this and get a number, and so forth. We keep looking at smaller and smaller and smaller and smaller time intervals. Mathematicians have shown, using what's called the epsilon delta argument, that for functions for the nice super duper well-behaved functions that describe the motion of objects in nature, that what will eventually happen is I keep taking smaller and smaller intervals, is that eventually the first digit of my answer becomes fixed and it never ever changes. And then if I keep doing smaller intervals, eventually the second digit in my answer quits changing and it will never change again. And then the third digit will quit changing and it'll never change again, and so forth and so forth. Now, if I do this forever, which is what this is saying here, I take I take the limit. I imagine doing this over an infinite number of these ever shorter and shorter time intervals. As these time intervals approach 0 difference, you end up with dx dt, the derivative of the position with respect to time. And if you haven't seen this in your calculus classes yet, don't worry about it. I will be introducing some of the ideas of derivatives as we go along. But this is literally the definition of the derivative, is we just keep taking ever smaller time intervals, calculate our average velocity for each of these time intervals, and we watch us get more and more and more and more decimal places. Now, as a practical issue, since physics is an experimental science, at some point you say, oh, hey, I've got 3 decimal places, I'm good. Or I have 5 decimal places, I'm good. Or I have 82 decimal places, I'm good. At some point, we don't need any more numbers than that. But this process of taking derivatives, and like I say, as we go along, I'll introduce the mechanics of how to do them as we need them, will allow us to say, even if I were to do this process an infinite number of times, this is eventually what the answer would head towards. So how do we interpret this sort of thing graphically? Well, let's imagine that I make a plot of position versus time here. So here's my position. Here's my time. I'm not going to write any numbers, so I'm not going to bother specifying units. If I have non-uniform motion, that's just a fancy way of saying it's not going to be in a straight line. So maybe it looks, I don't know, something like that. Maybe I can do a little better job with my art. Yeah, we'll call that good. All right, now let's say that what we're really interested in knowing is at exactly this time right here, we would like to know the what the instantaneous velocity is. And usually we'll just say velocity. If we just say velocity without qualifying it, that is the instantaneous velocity. If we mean average velocity, we'll always say average velocity. Well, what is our limit taking process all about? Well, we don't specifically look at this point, but instead we look at, say, a pair of points that flank it. And then when we took the displacement over the time, what that was the slope of this line segment right here. And then I could imagine doing this over a shorter time interval, say this one right here. And my next answer in my limit taking process would be the slope of that one, and so forth. So where is this heading to? Well, what we can imagine here is when I get to really, really fine intervals of time on either side, at some point to our eye, this is basically going to look like a straight line. It's like if you look at a picture of the Earth from outer space, it's curved, right? Because the Earth is basically a sphere. But if you are standing right along the surface of the Earth, so you basically got your nose right up against the curvature, it looks super duper flat, and you need instruments like lasers to be able to detect the curvature, because your eye just isn't good enough to do that. And mathematically, it's the same kind of idea here. If our position is changing, if the way our velocity is changing is doing anything sensible, so no instant jumps in velocity or something like that, which would be physically impossible anyway, then at some point, if I go to small enough time intervals, this is just going to look like a straight line. And what's that straight line going to look like? Well, it's going to look, pardon me here, like a tangent line to function. So this is our tangent line. And the way I find the tangent line, the tangent of a particular point, is if you have a ruler, you can lay the ruler so it's touching the point on the curve you care about. And you rotate the ruler back and forth, so at least in the immediate vicinity, you don't worry about what's happening far off. But in the immediate vicinity, the ruler only touches one point. Anywhere else you turn it, the ruler will end up touching some other point on the curve, and that's not a tangent line. So anyway, the slope of our tangent line here is our instantaneous velocity. And math professors will tell you that, in fact, for the derivative of any reasonably well-behaved function, will always give you the slope of the tangent line at a particular point. So, okay, we've got a so now we've got our recipe for how to handle if our velocities are changing. So what about if we need to take this in the other direction? So you remember before we took a look at the case of uniform motion here. So I'm just going to make a quick velocity time graph like so. Remember, uniform motion meant that the slope of the position time graph was a constant, or that the value of the velocity was a constant. So this time, let's say we're moving to the right. This would be uniform motion. And let's say we were interested in our displacement along, let's say, this time interval right here. So this is the amount of time elapsed delta t. What we saw before was that that was the area under the curve. All right, so now what if our velocity time graph isn't uniform? So if we have non-uniform motion, if I'm making a plot of velocity versus time, it's going to vary in some way. And thankfully, we won't have to worry about things like jump discontinuities and stuff like that, because again, we're describing objects that actually happen in motions that actually happen in nature. So again, here, let's just say now this is my plot of velocity versus time. And I am interested in knowing the displacement from, let's say this time it's from time 0 out to this final time t. So how can we do that? The recipe we had before worked if our velocity was a constant. Here, our velocity is never constant. We can play the same kind of game. So what we can do is we can imagine dividing this up into a bunch of very small time intervals. So let's say I'm just going to do a few of them to give us some sense of it. So what we can do is we can say the overall displacement. It's going to be the displacement over lots of these small time intervals that I'm drawing in here. And then what I can do is I can just kind of cheat. I can say if the time interval is small enough, the value of the instantaneous velocity at any given time is never that far away from the average velocity over that interval. So this would be the average velocity over this first time interval right here. So let's just say that's v bar 1, just so we've got some idea. Then we can do our area under the curve trick and say that for this small time interval right here, this is my displacement for this first time interval. And then I can play the same game here. I can say, yeah, that doesn't look that good. Let's try a little better. Yeah, maybe something like that. So then this would be the average velocity for my second time interval, and I play the same game. Find the area of this thin strip. And we'll do it one more time just for completeness sake. This would be the average velocity for the third interval. This would be my delta x3, and then what I'll do is I'll just add them all up. Delta x1 plus delta x2 plus delta x3 plus da 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 da, and eventually that will all equal the area under the displacement that I'm trying to find. So we're just imagining we're just going to continue this process on. Well, you might object and say, well, gee, that's great, but what you found was the area of these brown strips. That we can clearly see that at some points the object is going slower and then it's going faster, slower, faster, slower, faster. And I'll go, yeah, you're right. But if I've done this right, then roughly how much I miss by over here from me pretending it was going too faster than it actually was versus here where I was pretending it was going slower than it actually was. Hopefully these will roughly cancel. I mean, certainly I'll be making some small amount of error, but it may be good enough. Then you might object and say, well, what if I decide it isn't good enough? And I say, well, fine. Then what you do is instead of using strips this wide, you use strips, I don't know, 1/10 as wide, half as wide, something like that. Some thinner strips in any event. You go ahead and use some thinner strips, and you play exactly the same game. Now you're going to need, if you use strips that are half as wide, you just doubled the number of strips. But what that means is, again, the velocity will be the error that you're making by saying too slow versus too fast over the interval, because you're looking at a smaller interval, there isn't as much change to it, and so that error should get smaller. And mathematicians have proven that that is in fact the case. And so if you play this game where you keep making the strips skinnier and skinnier and skinnier, eventually you get to a point where the first digit in the final answer doesn't change ever again. And then if you keep making them skinnier and skinnier and skinnier, the second digit never changes. And then the third digit never changes. And then the fourth digit never changes, and so forth. And so what this converges onto is just plain the area under the curve that we had before. Except now it's the area under this irregular curve, but it's still just the area under the curve. Let me clean that line up there. There we go. So we can still say that our displacement is equal to the area under the curve, or again, we can say that this is now the definite integral from t initial to t final dt of the velocity, which would be a function of time. Now, if we remember, so that's the displacement, but we can also remember the displacement is x final minus x initial. So it'd be equal to that integral. And again, if you don't know what an integral is, I'll introduce what bits we need, but for us, it's just always going to be this area under the curve. I can add x initial to both sides and get that the final position is the initial position plus this area under the curve. Or if you prefer, just say it's the initial position plus the area under the curve. All right. So I'll introduce the integral taking as we need it, but for now, all I want to worry about is finding areas under curves. If you had something this horrendous, and you didn't know how to take integrals yet, you can do it by plotting the function onto a piece of paper, use an X-Acto knife to cut it, and then you weigh out the piece, and then you weigh a corresponding square whose area you understand, and you use the ratio of the weights to figure it out. But in more typical situations, what I'm concerned with is something that you can just use straightforward geometry to find. So as an example here, let's say that I have an object that speeds up from 0 to 20 meters per second over 10 seconds. So let me just plot that. Let's say that the velocity changes smoothly, or changes in a nice, well-behaved way. There we go. Boop, 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 boop. Boop, 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 boop. There we go. So we can say that the object starts at rest and goes to 20 meters per second over 10 seconds. And what I want to know is, what is the displacement for this motion? Well, here what we can do is we can say the displacement is the area under the curve. And here there's no real need to set up an integral. If you know how to do it and it makes you feel better, go ahead. But for what we need, we can just say it's equal to the area under the curve. And we say, hey, this is a triangle, so this is 1/2 the base times the height. So this will be 1/2 of 10 seconds times 20 meters per second. Now when I times the seconds against meters per second, what's going to happen? I'm going to have, let me just note this off to the side here. So seconds times meters per second, the seconds will cancel. I'll be left with meters, so that's good. And I have a displacement plus 100 meters. So the object moved 100 meters to the right, and I didn't have to take any integrals that I didn't want to take. Now, if you want, you could certainly go ahead and write a function for this. You could write that the velocity is equal to 2 meters per second and integrate it, but you're just integrating a count. This is easier here, at least for me. All right, but if we do have cases where the velocity is changing, we might want to start to be able to characterize how the velocity is changing, and the quantity we use for that is a quantity called the acceleration. And we do it in exactly the same way. So here I'm just going to do this in one dimension, so I'm not going to draw vector signs yet. They'll come in a future video. We'll define this to be the limit as time approaches 0 of the change in the velocity of an object divided by the time over which that velocity changed. And again, this is the exact same limit-taking process where we look at smaller and smaller time intervals around the time we care about and see what we converge to. So this is a derivative. So we could also write this as dv dt. So the units here, this is meters per second. I'm dividing by seconds, so the units here will be meters per second per second. We usually write that as meters per second squared. All right, so can we try to get at least some sort of graphical intuition for this? Sure. Let's just say we start by having an object that is speeding up, moving to the right, like so. So I'm going to draw these little arrows here that indicate how fast it's going. The official name of these arrows are vectors. And so the idea is to indicate how fast something is going and which direction. I can indicate the direction by just literally the direction the arrow goes. And I can indicate how fast by how long I make the arrow. And graphically, I can add and subtract vectors so if I want to add two vectors, we'll do more on this in a later video, but just to introduce the idea now, let's say here, the idea is that we know that the change in velocity would be the final velocity minus the initial velocity. I can rewrite this to say the final velocity is the initial velocity plus the change in velocity. So how do I add two vectors? It's just literally you stick one on top of the other. So here I can say this is my initial velocity. I will add to this. I'll draw it in blue just to make it a little more obvious. There is my change in velocity. Now what I've done is I've added these two. By adding these two, if I connect from the tail of what's over here, the unconnected tail here, to the unconnected head there, that is my final velocity. This is an example of what's called tail to head addition. So v initial plus delta v gives me this. All right. I can also say, well, what would it mean to have a negative arrow? A very natural way would be to say the arrow points the other way. And so that would be indeed correct. So if I had my final velocity, my initial velocity here, what I can do is I can take my final velocity And what I'll do is I'll add to it the negative of my initial velocity. So what I've done is I've taken this arrow, preserved its length, and just flipped it exactly backwards. And this is what I mean by a negative. And I put the tail of this to the head of this. Now, theoretically, I should lay the one right on top of the other, but if I do that, the drawing will get confusing. But then if I go from the tail of the unconnected tail to the unconnected head, I found my change in velocity. Well, my acceleration points in the same direction as my change in velocity, so I can then conclude in this case here, if I'm moving to the right and I'm speeding up, that we must have it that the acceleration, that the object was accelerating to the right. All right, so now what if instead of hitting the accelerator, you hit the brakes? So let's go ahead and look at a motion diagram for an object that's slowing down. All right, so here, if I look at this interval right here, this would be my v initial, and then I'll have a smaller v final. To find my change in the velocity, I could do exactly the same recipe we did before. I put down my v final. Now I add to that my negative v initial, and we will do much more with this graphical stuff in a later video, but I'm just doing this right now to introduce the idea. And what we get, drawing the unconnected tail to the unconnected head, is that the velocity is changed, that the change in the velocity is pointing to the left. This kind of makes sense. In a certain sense, an arrow that's pointing to the right not as strongly as some arrow that's pointing to the right more strongly is in some weak sense pointing more leftward. It just hasn't pointed left yet. And so that's what this change in velocity is indicating. It also tells us that the acceleration is pointing to the left. So here, in all these cases we looked at, the velocity was pointing to, this has always been pointing to the right, but here, when we were speeding up, it wound up pointing in the same direction as the velocity. And here, when we were slowing down, it points in the opposite direction of the velocity. And by the way, these aren't the only possibilities. When we get into two-dimensional motion, if we have an object that's going around a curve, we'll find that the acceleration can point to any which way. But at the moment, I'm just concerning myself with moving, just changing speed along one dimension. And so that's how we can interpret our accelerations. If it's pointing the same way as the velocity, that means you're picking up speed. And if it points against the velocity, it means you're losing speed. All right. So let's start to see what this looks like if I make different velocity time graphs and how I would interpret these. So, for instance here, let's there we go, velocity time. Gonna make a bunch of these, so let's just copy that real quick. Copy, there we go. So now let's go ahead and say that my velocity time graph looked like that. Well, I can look at this and say the velocity is positive. And how do I know that? Simple, it's always in positive territory. This is a v versus t graph. All the values on here are positive. So the velocity is positive. What about the acceleration? Well, to get the acceleration, I'm going to need to look at the slope of my velocity curve. And I can say that because we said that the acceleration is the time rate of change of the velocity. So just like when we looked at velocity, it says time rate change of position and came to the conclusion that's the slope of the graph, we can do exactly the same thing here. So here my slope is positive, so we conclude that our acceleration is positive. If I were to draw my vectors here, which we will do more with in a future video, my velocity would be going to the right, and my acceleration would also be going to the right. So if I look at this, it's saying I'm moving rightward and I'm picking up speed. Okay. What if instead let me move that there, yeah, there. So what if instead my velocity time graph looked like, let's say, whoops, this. Well, again, the value of my velocity is positive, but now if I go and look at my slope, my slope is negative. So I conclude that my acceleration is negative. So if I draw the vectors, you would be saying that the object is moving to the right, but its acceleration is pointing to the left. All right. Let's go look at a couple more cases here. Oops. So now let's go look in quadrant 4 for a bit. So this is my velocity. I'll extend it up just a little bit right there. There's my velocity. There's my time. We'll copy that as well. All right. So my curve, let's say looks something like that. Well, here now my velocity is always negative. What about my acceleration? Well, I can get the slope of the velocity time graph here and get that the slope is positive. So here my acceleration is positive. So here I'm moving to the left, but I'm slowing down. So that gives me a positive acceleration. And if I look at my vectors here, so I mean that my velocity vector is pointing to the left, and my acceleration vector is pointing to the right. So again, what we say is if an object is slowing down in one dimension, its acceleration always points in the exact opposite direction as the velocity. So this makes some sense. All right, and then finally, oops. There we go. Put that there. There we go. Let's look at the this one. So my velocity time graph, let's say, looks, there we go, something like that. So here my velocity is again negative because we're in the negative part of the graph. And to get my acceleration, I look at the slope of the curve and see that it is also negative. So that means the acceleration is also negative. If I were to draw vectors here, this would be telling me that the object is moving to the left. And since it's picking up speed, the acceleration is pointing also to the left in the same direction. Alrighty. So this leads us to a collection of prototype graphs that are very much worth having in your back pocket. The prototype cases that are worth knowing the graphs for are constant constant velocity and constant acceleration. Now, technically, constant velocity is also constant acceleration, because if your velocity isn't changing, then that means your acceleration, which is the rate at which the velocity changes, is 0, which is a constant value. But it's useful to think about the case of constant acceleration where the acceleration isn't 0. So that's what I mean here. All right. So let's go and there, I'm going to need 6 of these. Copy, paste, paste. There we go. Paste. That looks pretty good right there. Paste. And paste. All right. So you see these graphs here. I am going to be plotting A versus T, V versus T, and X versus T. So, in the case of constant velocity, the velocity is a constant. You'll have a horizontal line for the graph. And like I was mentioning, since the acceleration at any time is the slope of the velocity time graph, that would mean that specifically the acceleration would be 0. And here, since the velocity is the slope of the position time graph, if this value never changes, then that means the slope of this never changes, and so you'll have a straight line for the position time. Now, there are, as we saw playing with this kind of thing earlier, that we can have this, say, pointing down, and then this would be a negative number or whatever, but the main thing I want you to get is this will be a straight line, this will be a flat line, this will be 0 if the velocity is a constant. Now let's say the acceleration is a constant. Well, in that case, this will be a flat line, and we're looking at the case of it not being 0. Well, again, it's the same deal. The velocity is the slope of the acceleration is the slope of the velocity time graph. So if this never changes, it means the slope of this never changes. So you're going to end up with something that looks like this, just constant slope. But now here's where it's a little trickier. The position is the velocity is the slope of the position time graph. So if I look here, I can see that over here, the slope of the curve here has to be smaller, and over here, where this value is bigger, the slope has to be bigger. And so what I'm going to end up with is something that looks like this. And this shape is known to mathematicians. It's a parabola. Now, one thing that's useful to remember here is we've said before, so if you've seen derivatives, remember we have said that the acceleration is the derivative of velocity with respect to time. And similarly, we said that the velocity is the derivative of position with respect to time. This means that we can also write that the acceleration is the second derivative of position with respect to time. And in math classes, what they'll do is they'll show you that a second derivative tells you what the curvature looks like. So for what we need, what we can take from this is if our acceleration is positive, the shape of our parabola will be one that holds water. And if our acceleration is negative, then the shape of our parabola will be one that spills water, like so. It might not be the entire parabola, but whatever section of parabola we have will follow the hold some water or spills water shape correspondingly. Alrighty, so in the next video, we are going to start to look at the situation of what if the, for cases where the acceleration is a constant, leading up to what I like to call the gang of four kinematics equations. Although this won't cover every possible kind of motion, a lot of times at the very least we can break up motion into time intervals where the acceleration is constant or constant enough. The notorious exception of this being things like launching rockets, where you actually have to start worrying about higher derivatives of position. For those of you curious, the third derivative is the jerk, the fourth derivative is the snap, the fifth derivative is the crackle, and the sixth derivative is the pop. And yes, snap, crackle, and pop are named for the characters from Rice Krispies. But we won't have to worry ourselves with that. Most of the time we can just get away with characterizing the motion, at least as collections of periods of time where the acceleration is a constant. So it's a very important case to study, and that will be where we'll be turning our attentions to next time. So catch you over there.